Good day, everyone. Today we'll be learning about the distribution of active volcanoes and major mountain belts. The most essential learning competency for this lesson is to describe and relate the distribution of active volcanoes, earthquake epicenters, and major mountain belts to plate tectonics theory. For the objectives, at the end of the learning process, you are expected to: number 1, identify and locate the active volcanoes, earthquake epicenters, and major mountain belts in the Philippines. 2, perform simple calculations to locate the epicenter of an earthquake. 3, analyze and interpret graphs related to an earthquake's epicenter. And lastly, relate volcanoes and earthquakes as viewed in the plate tectonics theory. Let us start with recalling your grade 8 science on the concept of the plate tectonics. Let us take note here of the two words plate and tectonics. Plate referring to the large mass of land that composes the Earth's crust, while tectonics refers to the movement of these plates. In the picture are the plates that compose the Earth's surface. The Earth is made up of small and large plates. According to the plate tectonics theory, the plates are moving constantly and slowly. Let us take note here of the two important words, constantly and slowly, meaning the movement of the plates still happens in the present. This is an animated picture that shows how the plates are moving constantly and slowly. From geological evidences, the Earth is believed to have a single plate called Pangaea, which has been broken to smaller plates through time. To understand the idea of plate tectonics theory, let us recall first the layers of the interior of the Earth. The innermost layer of the Earth is what we call the inner core. It is made up mostly of solid iron. On the other hand, the outer core is made up of molten iron. This layer of solid rocks is what we call the mantle. A special layer at the top of the mantle is what we call the lithosphere. It is made up of a portion of the crust and a portion of the mantle. And lastly, the crust is the outermost layer of the Earth. Due to the high pressure and temperature in the inner core, rocks in the mantle become melted and moving, causing the crust to move thereof. With these various layers of different composition, the heat from the inside intends to move out of the Earth to prevent collapsing of the planet. The very hot core melts rocks in the mantle, moving upwards, causing the plates to move separately towards each other and slide past one another. Here is another illustration that will explain how the plates move due to the interior of the Earth. The core here provides very high temperature, which allows the rocks in the mantle to melt. Warm rocks move upward, while cold rocks move downward, forming a circulation of these molten rocks called the convection cell. This convection cell, or the circulation of the rocks, is what pushes your crust away from each other, eventually moving plates towards one another or sliding past another. This animation gives us a good look of what happens in convection. Moving upwards are the molten rocks of the mantle due to the core's heat. As these rocks move, it pushes the lithosphere in motion, causing plates to collide, separate, or slide past one another. This lesson on plate tectonics will focus on the impact of the movement of the Earth's plates. Relatively, it will discuss the earthquakes, volcanic activities, and the formation of mountain ranges. Let us recall first the concept of earthquakes. Earthquake releases three types of seismic waves, namely primary waves or the P waves, secondary waves or the S waves, and long surface waves or the L waves. Moreover, these waves are what produces the impact we perceive as shaking and moving of the ground. The picture depicts how waves are formed from an earthquake. The very main source of an earthquake is what we call the focus. From the focus radiates different kinds of waves, represented by these red circles. Waves which travel in the interior of the earth are called the primary waves and the secondary waves. They are collectively known as body waves, while waves moving at the surface of the earth's crust is what we call the surface waves. Directly above the focus of an earthquake is the epicenter, while cracks and breakage at the crust is what we call the fault. So how do we identify the location of the epicenter of an earthquake? Seismologists use a method called triangulation. In the triangulation method, given the difference in the arrival time of P and S waves, we can identify the distance to the epicenter of this station. Moreover, from the distance to the epicenter of these stations where we perceive the P wave and the S wave, we can now identify the epicenter of the earthquake. Here is an illustration of how triangulation method is done. After distances from at least three seismograph stations, namely Tokyo, Anchorage, and Berkeley, are determined, they are platted as circles with radii equal to the distances on the map. So what we have computed here as the distance to the epicenter gives us the radius of these circles. The epicenter is the point at which the three circles intersect. Given is the formula in which we can find the distance of the stations from the epicenter of the earthquake. We have here TD, or the time difference in the arrival time of P and S wave in seconds, multiplied by 100 kilometers divided by 8 seconds. Values such as 100 kilometers and 8 seconds are constant for this formula, since we are assuming 8 seconds of interval between the arrival of P wave and S wave at a specific distance of 100 kilometers. So every 100 kilometers, P waves and S wave arrived with an interval of 8 seconds. Let's have an example of how triangulation method is done theoretically. Given our recording stations Batangas, Puerto Princesa, and Davao. From these stations, we have recorded time difference in the arrival of S and P wave as 44.8, 32, and 38.4 respectively. Using the formula above, let us identify the distance of epicenter from the station. We have here D is equal to 44.8, which is the time difference in the arrival of P wave and S wave from Batangas, gives us 560 kilometers as the distance of Batangas from the epicenter of the earthquake. For Puerto Princesa, we have 32 times 100 divided by 8, which is 400 kilometers, giving us the distance of Puerto Princesa from the epicenter of the earthquake. And lastly, for Davao, we have 38.4 times 100 divided by 8, gives us a distance of 480 kilometers as the distance of Davao from the center of the earthquake. Let us now plot these computed distances such that these values are scaled to the radius of a circle around the given situation. Here is a Philippine map where we are going to plot the different distances. So we have here stations Batangas, Puerto Princesa, and Davao. Let us assume a scaling of 100 kilometers is equal to 1 centimeter. From the computed values of the distances of the station from the epicenter of the earthquake, let us identify the radius of the three circles from these three stations. So we have here 5.6 centimeters from 560 kilometers, 4 centimeters from 400 kilometers, and 4.84 centimeters from 484 kilometers. So from this radii, let us illustrate three circles, again around Batangas, around Puerto Princesa, and around Davao. Take note of a single point where these three circles intersect. This single point is what we call the epicenter. So meaning, the earthquake came from this single point called the epicenter. Let us now consider the graph of the S wave and the P wave. How do we identify the distance of these specified stations from the source of the earthquake or its epicenter? Given this graph, so this is the graph of the P wave, the travel time of P wave, and the travel time of S wave. The difference in the arrival time will tell us the distance of the earthquake's focus from the seismic recording station. So the distance identified here as the distance between S wave and P wave arrival gives us the idea of how far these stations are from the epicenter of the earthquake. The larger the difference, in this case 5 minutes, gives us an idea that the station is farther from the epicenter of the earthquake. Again, the farther apart the arrival times of S and P waves, the farther away the epicenter of the earthquake is. Now, let us locate the earthquake zones, volcanoes, and mountain ranges. Where can we find them? Let us take a look at this map of the 20 largest earthquakes in the world. Illustrated in the red dots in this map are the locations where earthquakes has occurred from 2000 to 2009. The 20 of the most destructive and strongest earthquake is numbered from 1 to 20. What can you say about the locations of these earthquakes? Are the locations random? Do they follow a certain pattern? Next is a volcanic map of the world. Plotted here are the most active volcanoes in the world. What can you say about the locations of this volcano? Are the locations random? Do they follow a certain pattern? Lastly is a map of the world's largest mountain ranges. Most common among these mountain ranges, of course, are the Himalayas. Others include Andes and the Rockies. In the Philippines, we have our very own Sierra Madre. What can you say about the locations of these mountain ranges? Are the locations random? Do they follow a certain pattern? I bet you already have the idea of the locations of these earthquake zones, volcanic activities, and mountain ranges. Let's have a recall of the section of the lithosphere having the planes which are constantly and slowly moving. When they move, they may collide, be separated, or slide past each other. So what happens upon the motion of these plates? The movement of these plates can cause vibrations or earthquakes or produce various landforms such as volcanoes and mountain ranges. Illustrated in the picture here are the different plates which can be found in the Earth's surface. The Earth's lithosphere is divided into about 13 major plates, where plates collide, separate, and slip past one another at plate boundaries. Interesting geological activity results. These geological activities are what we know as, of course, the earthquakes, volcanic eruptions, and the formation of landforms such as mountain ranges, mountains, valleys, and others. These activities or phenomena can be found on a single pattern that we have as the edges of the plates. Remember, the interaction between and along the plate boundaries resulted to frequent earthquakes at those locations. Strong earthquakes are more likely to occur along active plate boundaries. An example is the San Andreas Fault in California. Also, the interaction between and along the plane boundaries resulted to frequent volcanic activities at those locations. In the Philippines, a remarkable occurrence of earthquakes and well-remembered volcanic activities. In here are found also majestic and famous landforms. These features and events can be accounted to the location of the country called the Pacific Ring of Fire. The Pacific Ring of Fire is emphasized in this map. It covers the border of the Pacific Plate. 75% of recorded active volcanoes are found along the Pacific Ring of Fire, while 81% of earthquakes here originated from this ring too. It is a region of high volcanic and seismic activities that surrounds the majority of the Pacific Ocean basin. It is made up of converging plates that borders the Pacific Ocean. This has become a good source of information for decades on how volcanic activities relate to the plate motion. Are there any questions? This ends our lecture on plate tectonics and earthquakes. We'll continue learning more about volcanic activities and mountain ranges on our next lesson. Have a good week!